Hi everyone! I know the first cohort of students who are taking the new physics syllabus are coming. So there are not a lot of resources out there. So I created this mind map to help you revise for the new syllabus. This is my new series, okay? And so for today's video is only focused on the mechanics. Mainly is on topic A1, 2, 3, and D1. So let me just have a very quick introduction here. Obviously, we'll be going through the mind map in this video, and the importance of having this video is then you understand the sequence, so where to start, how it gradually evolve, how the things get logically deduced, etc., and also the details. And this is a very essential revision task that I always do with my class in school with the whiteboard, and I took the effort of more than I thought. I think I spent about a day, more than a day, to make these digitalized mind map on Figma. And so hopefully you'll find it useful. The PDF version of it will also be shared in the description, so you can download it. You can then digitally annotate it. I'll show you how exactly you can do it, so then it support for your revision. The file is only intended for educational use, and you should not be using it for commercial purposes unless you get my permission. I'm saying this because I have bad experience before. Okay, someone stole my work and then just use it for commercial use. Anyway, so this is a tool for you to revise. It doesn't mean everything, okay? So you still have to do probably more practices. You have to understand by reading the textbook, etc. But these should be quite good enough if you're having a quiz or assessment and you want to consolidate your idea better, and also making sure that you're not missing any requirement from the syllabus. There might be mistake, although I try to avoid it, and obviously it's not perfect. Okay, for drawing a mind map, there's always a different way. Every person can have different way to do it, and so if you have any suggestions to make it better, please let me know. Okay, and I may update the PDF, continuously, so that everyone here can be benefit. As a teacher, okay, other than just following my mind map and then going through that as more like a checklist or so, I will also encourage you to build one. And in fact, when I am doing it, I also get myself to really rethink, okay, everything when I was delivering the curriculum to my students. And so I believe it will be very useful to you as well. Okay, so no matter you do it with pen and paper or digital tools, it will still be fine. Okay, you really will be learning even more, okay, if you can build one by yourself. Okay, that's the first principle we are always talking about in physics, and then you can come back to compare it with the mind map that I built. Okay, maybe you build an even better one. If you think this video is very useful, okay, please share it to your friends and let me know in the comment, so I have the motivation to complete this series. I'm planning to do the whole syllabus, hopefully, and so this is the first one which cover mainly the mechanics. The way that I'm doing is just simply the way I design the curriculum, the sequence that I will do at my school. It may not really reflect in yours, but I believe that it should be quite logical enough, and it should be quite the mainstream way. Okay, so we'll go for the mechanics, and then hopefully, okay, if I don't procrastinate, then we'll get to the electrical and magnetism part, and also afterwards will be the waves, and then the thermal, and then at last the nuclear fusion, nuclear physics, and at last, okay, which is the 𝐁𝐚𝐬 part for the mechanics, the relativity, and also rotational kinematics. And so for each video, I'll try to cover the SL part first, okay, because the new syllabus is a bit different from the previous. I don't want to explain too much, but basically I want to save the SL student from going through something that is somewhat irrelevant to them directly. So everyone can watch the first part, and if you're 𝐁𝐚𝐬, then you stay with me until the end. Alright, let's get to the mind map. So this mind map, I built it on a platform called Figma, or their tool called FigJam, and I believe this should be the best tool for building a mind map, okay, across the different one that I try. And but then I'm not sponsored, okay, I'm not sponsored by them. You can see I'm using the free version only, okay. But I'm totally okay if you want to sponsor me, okay, Figma. All right. Anyway, let's go to the very general idea first, because I have a bit of idea on how the different symbol will mean different thing. So my student will know very well. In my notes, I always put the SL content as green color. So we'll go for the green color first, and then the yellow color will mean the 𝐿. And then in physics, I also think that it's quite important to understand things that are being defined, which pretty much you can't really try to look up how it's being, a deeper origin of it, okay, and then versus the other one that is being derived, okay. So things get defined first, and then from those definition or axioms we call, then we can have some new equations or new concepts, okay, which are called derived stuff. So the symbol I use, I just created on myself. I know there are more complicated symbols in computer science and other field, but I just do it in a way that is easy, okay. So think about a rectangle, okay, and then its definition is sharp, okay. You don't want to argue with it, okay. And then what you can do is, if you take that and you trim it off, okay, then you get something new, okay. So that's derived, okay. This is why I use the rounded rectangle for derived. Okay, and then there's a very tiny bit of stuff that are actually out of syllabus, but I do think it's important to mention it. Okay, so then it's listed as a gray color here. All right, and so in the coming video, I will then be using an emoji to just indicate that we have gone through that part. Okay, but then I do think it's a good way. So when you are doing it, going through the mind map yourself, what you can do is you open a new file, the PDF file, and then you either, I don't know, circle it, put a tick, or whatever sticker that you put it on with whatever tool you use. I think that would be quite helpful, okay. And also maybe you also can consider having a different way to annotate, for things that you are very confident, you put a tick, and for things that are unsure, maybe you put a question mark, or for the things that you find something you might forget, then maybe put a star or something, okay. So that would be quite helpful, okay, when you revisit the mind map again. All right, let's get started. So physics start with observation, okay, and the easiest observation that you probably would make, and also the most interesting thing, is how things move, okay. So motion, and that's kinematics. And we want to describe it with a scientific idea, so we have to quantify them, we have to describe them in a common language. So we use displacement, velocity, acceleration to describe them. These are vector, and distance and speed will be the scalar. We focus more on the vector side, and so these are the definition, okay. Displacement, velocity, and acceleration. So velocity is change of displacement over time, acceleration is change of velocity over time. And so with that, we get very soon in your first topic A1 your kinematics equation. These are the four equations only if the acceleration is constant, okay. So you can only use it, okay, when it's constant. And this is something that some students may overlook. And what if it is not, okay? If it is not a constant, then IB will require you to describe it qualitatively, okay. And so it will come to a point where you will talk about terminal velocity, and then maybe the graph, how the air resistance will change. One essential idea will be something related to how the net force becomes zero, acceleration zero, and velocity being constant. We'll get to that point again later on. If you want to go for a more quantitative approach, which is not required in IB physics, then what you need to do is you have to use calculus. Okay, so for those people who study engineering and physics in the future, you get to it. Now, going back to the kinematics equation, we also have the three ideas like the displacement, velocity, and acceleration. Don't forget, we also need to know how they are presented visually and also how they're related to each other. So for example, if you want to find the velocity, you look at the slope, okay, of the distant time graph, and if you want to find the acceleration, you look at the slope of the velocity time graph. In reverse, okay, you look at the area. So the area under the curve for acceleration time graph will be the velocity change, and the area under the velocity time graph will be the change of displacement. At the same time, you are also required to know the difference between instantaneous and average. I suppose you know it. All right, and then now you probably you were learning about the 1D, one-dimensional motion. So either left and right and or up and down. And then very soon you get to the projectile motion, which is in 2D. And so you will then have to consider them as vector. So you have to resolve them vertically and horizontally and deal with them using the same equation. And so whenever you see these, we'll get to see them again in forces and other places. But then do remember we'll have to use trigonometry. Okay, so taking cosine or sine if you want to decompose them or resolve them into the two components. I'm not going to repeat this diagram again, okay, but I'll remind you again when you might get to see 2D problem. Now, when it comes to projectile motion, you are also, of course, you have to do a lot of calculations on that. But in terms of the situation where you have the air resistance, okay, or fluid resistance, IB only require you to do it in a qualitative way. So how the trajectory, for example, the velocity, acceleration, range, and time will be affected, as you can see here. Okay, this is a diagram which you may also find in my video or your textbook. The blue one is without air resistance, it goes further and also symmetrical, and also the red one will be with air resistance. So it go the highest point is lower, the range is shorter, and then it is asymmetric. Okay, and you can also look at the velocity as well. Now going back to the terminal velocity, then you might have to consider how the air resistance, I think it will be a good starting point, although you can apply on other things like fluid resistance, how the speed itself would increase the air resistance and eventually making the deceleration greater. So again, I'm not putting the details here, but if you're not very familiar with it, then you should go back and revisit my video or your textbook. Now, I think we should be good to go to look at the other branches. So we have done just the kinematics part, and then now we are looking in more details. And so in terms of motion, in fact, other than kinematics, we can also use different approach to determine or predict the result. So one way is to use force, which we'll be looking at it very soon, and then you can see energy and momentum later on. So for forces, okay, you first will find there are different types of forces, okay, which we'll go through soon. And no matter what force you are talking about, you should be able to represent them by using something called free body diagram. When you draw a free body diagram, you should pay attention to the length, which represents the magnitude, and also the direction. One thing that I find students usually forget is the point of application. So where exactly do you start to draw them? For example, the weight should be drawn from the center of mass of the object. Friction should be drawn between the two surfaces, and not to forget the correct label as well. Okay, so the name or the symbol as required by IB. With that, then we can then resolve the forces for analysis into two axes, either X or Y, horizontal, vertical, or sometimes you may have an inclined plane, as you can see in this diagram. Then you have to decompose again using trigonometry. I'm not repeating myself here. Talking about the inclined plane, I recommend you to memorize, I should say, the result that's mg sine theta going along the plane, while the one that's perpendicular will be mg cosine theta, if theta is the angle. Now going back to the type of forces, so in IB they literally just flowing at you with different forces. So there are lists of forces that you have gone through. The first one is normal force, which you get to see very early on. Is always perpendicular to the surface. And then one thing that I feel my students don't really get very well is it's very passive. So you have to understand whether or not the system is having acceleration or not, and then how the other forces are acting on the system. And then the normal force is very often the most passive one. Okay, so it's a consequence of so many other things in the end. So it may increase, it may decrease, it may get to zero. It cannot be negative, however, okay, depending on other conditions. We have other forces, friction, okay, which I'm sure you all know. And then there are two types, static and dynamic, okay, which leads us to the two equation. And then elastic force, okay, which is a spring, for example, which follows the Hooke's law for the very first part, following the proportionality limit. And then you can apply Hooke's law, which is using the linear model to model it. And then we have also got to the viscous drag force. There's an equation describing it. One thing that you may overlook is only apply for small sphere. It has to be a sphere. That's why there's an R in it. R represents the radius of the sphere. The symbol, okay, that you may find quite unfamiliar here is the viscosity. Next is the buoyancy force, which if anything that is submerged in a fluid, even if it is like reaching to the bottom of a container, you still have that buoyancy force. As long as you have displaced the fluid, you have that. And then you have the equation here. The V is how much volume displaced. You can also take it as how much volume that being submerged in the fluid as well. The rho is the density of the fluid. In terms of the equation, I don't think I'm going to explain every single one of them in so much detail, because in the future I'll also be making another video similar to the old syllabus called going through the data booklet. So I'm skipping the details in the future. Now scrolling to the other types. So the thing that we just now mentioned are all contact forces. So going back to think about all these forces, can you do it without having a physical contact with between them? Not really. So if you really have to put them at a category, then contact forces. However, the bigger idea, in fact, in physics is the non-contact forces, which they also can be described by field lines because it's rather abstract. So again, you probably have known it already: gravitational force, electric force, and magnetic force. There are some other forces as well, but these are the part where we want you to get into in this field subtopic. So we shall first go back a little bit first, okay, I think, sorry about that, okay, to look at the Newton's law, okay. So before you get to the very detail of the gravitation, you should have heard about the Newton's law. So first law is talking about how the object are not experiencing an unbalanced force, will be staying at rest or with a constant speed. So the definition here, okay, you can see I put a really long sentence here. There's a reason for that, okay, because basically you have to recall it, okay. So you literally can just follow my wording here, okay. If you have no idea, or if you want, you can revisit your textbook, or you can go, perhaps can find somewhat there is a past paper question and looking at the math scheme. But my point here is knowing the word definition is essential. Okay, so the Newton's first law basically gives us the idea of how a system can be in translational equilibrium. I say translational because some of you, if you have learned A4, you know there's rotational. Okay, so the things we are talking about is only translational movement. Now, more generally speaking, we have the Newton's second law, which you may think is F equals ma, but in our video earlier, okay, I put a link here. I think if you're opening your PDF, okay, you'll be able to find this with a hyperlink which link to one of my video, and then in that I explained that the definition of second law in fact is saying the net force is the rate change of momentum. Okay, it's not MA. Okay, MA is only a specific case of it. Okay, this is a more general, okay, more fundamental, therefore. Okay, and of course, the reason why when we do F equals MA, which is applicable in most of the cases, is because when mass is a constant, then the equation will be reduced to be F equals MA. All right, we'll get to circular motion later on. Okay, but let's finish the Newton's third law first. So the third law basically are telling us that force come in pairs. Again, I feel this definition is often overlooked by students. Okay, so let me make it clear. So the forces we are talking about is when A exert a force on B, B also exert a force on A. Okay, it's two objects. It cannot be the same object. And then the forces will be in equal magnitude and opposite direction. Okay, again, this may be asked, okay, directly as a word definition in the assessment. One example, I don't often put example, but this is a one I really want to clarify. So for example, the gravitational force now you are experiencing that pulling you down by the earth, okay, is having a pair of force. That's also the gravitational force. Okay, remember, it's not the normal force. Many students think it's a normal force. Gravitational force that's acting on the earth by you. So you are pulling the earth upward, okay, in some way, although it's not very significant because the earth is very heavy. Now we can get to the circular motion, I believe. Okay, and so coming back to F equals to MA, okay, and then normally you probably are doing like things in, translation or like in a straight line, so horizontal, vertical. But if it is moving in a circle, then we have learned a system to deal with that. So first of all, by definition, we have now two velocity. Okay, the one we normally use as V is called the tangential, or some people call it the linear velocity, which is defined by 2 pi r over t, and then for angular will be 2 pi over t. Okay, so you can see it's missing by an r, and therefore you have an equation like that. The data booklet does not really show exactly like this, so I recommend you to also maybe write down somewhere on your data booklet or in your revision notes, so then you can clearly understand. Okay, so these two are defined, and therefore you can derive the data relationship. Now in IB Physics, you're expected to know both uniform and non-uniform circular motion. Okay, and so when you have a uniform one, that's because there's a net force, which is a centripetal force, okay, pointing towards the center, which is most of the cases that you encounter. However, there are also cases where the net force, remember the net force can be composed of more than one force. Okay, it's not just maybe a tension or something. It can be the tension and the weight. Okay, that is not pointing towards the center, so maybe it's off from the center, and therefore if you try to resolve it, there must be a tangential component presented. In this case, then the speed cannot be maintained the same. There must be a change, either increase or decrease. Okay, and so in those cases, one of the example could be a vertical circular motion with a string. So again, if you want, you can refer to the video, or in a very simple diagram, okay, you can refer to this here. As you can see, at the top, the forces, okay, will be different, and or maybe just don't even look at the equation, just look at the two arrows. Okay, at the top the arrow are pointing downward, okay, both of them downward. At the bottom is still pointing towards the center, but the magnitude is different. But the most important thing is on the side, left and right, as you can see, there's weight, there's tension, so you can see the force that you must be going in this way or this way as a resultant force. So it's not pointing towards the center, and therefore it's a non-uniform circular motion. All right, and then for the equation that we have, we are going to only use it for uniform circular motion, okay, which therefore you have a centripetal acceleration, okay, still pointing towards the center. And so the expression is here. just one thing I forgot to mention here, okay, is the frequency equation. Frequency equals to 1 over period. I think everyone know if you have learned waves before, and this will give variation. Okay, so this is from the data booklet. There are 3 versions, 1, 2, 3. Okay, choose one that easy for you in a different question. But at the same time, don't forget there could be a 4th variant, okay, that is taking the period and then changing it to frequency accordingly. Now, one example for uniform circular motion is an orbital motion, which you get to see a lot, especially if you are 𝐿. And then for orbital motion, there are 3 Kepler's law, which describe an orbital motion. I put it in this way because of make it easier for the mind map to display. The first law is the law of eclipse. So basically it's saying that the orbit is actually not circular, okay, it's elliptical. So there are 2 foci, okay, the sun is at one of the foci. So it's more like a fact, okay, from the observation. Now the second law, which is also related to, if you're in 𝐿, you learn about angular momentum, okay, in A4, then you understand. If you don't, it's fine, okay. But basically the law is saying that the area swept by the planets, okay, over the same amount of time will be the same area. So essentially, I think it's easy to understand visually. So you can see this diagram, okay, I took it from Google, and then you can see area 1 here versus area 2 here is the same, if only the time is the same. Okay, this is a very interesting consequence of the motion equations. The very last one from Kepler, third law, is to state that the relationship of the period and the radius of the orbit is like this, okay. And so when Kepler was observing, it was more like an observation, really. He didn't know why, okay. But then the good thing about this is it really matched with the result from Newton's theory, which we'll go through the equations later on. And so yeah, it's just so amazing to see that the observation, and then there's more like a theory or hypothesis, and then later on supported by another scientist. All right, now so we have finished the circular motion, and let's go back a bit. Okay, we would want to go for gravitation, but for the sake of the usual way that you studied, and I would like to go for energy first. Okay, so coming back to the way that we can determine motion, okay, other than force, we can also go for energy. Okay, so here I put question mark here because I just find it's just a bit strange to put in the curriculum, but that's why I have this mind map, I guess, okay, which is called the energy density. Is the unit is joule per meter cube, okay, so you can use the idea of density, mass over volume to sort of deduce this unit. And so this is referring to things like the different resources like the fossil fuel, the nuclear fuel, those things, like how the density would be different for different sources. But it's a very applied idea. But going back to a more fundamental idea, first thing is we want to introduce you with different types of energy, not all of them because of the time, but the important idea is they would then obey the conservation principle. And then the very first idea we come into mind should be work done, which described by this equation, and then it helps us to derive the 3 mechanical energy equations in a system, namely kinetic energy, GPE, and also elastic potential energy, in which is provided in your data booklet. Okay, I'm sure you all know them. Just pay attention that the GPE equation mg delta H is only working for near the surface of the planet. So 9.81, for example, for Earth, because the G will be changing, okay, which we'll address very later on, especially your 𝐿. So now in the mechanical system, other than these free energy are interchanging, maybe KE turn to GPE or so, in reality, we also have friction. So work done against friction and then eventually turning to thermal will be the reason. You can do calculation, of course, okay, by simply plugging in the friction, and if you know other parameter, then you can also calculate, okay, you can quantify it using the work done equation. And that would bring us to the idea of efficiency issue, okay, in a system. And so together with the idea of how energy is delivered in each second, we have the concept of power, which I'm sure you all know, okay, with this equation. Work done over time is the fundamental idea. F times V is a more like a derived idea, okay, which I didn't make it very explicit here, but I'm sure you are all okay with that. Efficiency, okay, there's an equation. You either can use energy or power ratio, okay, the useful one divide the total one to calculate, okay, it's dimensionless quantity, okay, so that's why I have the two arrow here, okay, which lead us to the Sankey diagram. Okay, a Sankey diagram again should be quite straightforward to IB student. The main thing is you have to pay attention to the scale. Okay, the energy that going forward are useful, the one that going down are wasted. Going on to the next one, we finish energy, so now we move on to momentum, another big main way to look at motions. So is quantified by mass times velocity, okay, this equation. And then the interesting thing about momentum is the momentum will conserve if there's no net external force. This is done by observation. And this, in fact, again, aligned with Newton's third law. You can use Newton's third law to derive the conservation of momentum. And there's an equation if you want to use, okay, how m1 v1 m2 v2, okay, and then equals before and after conserve, okay. So momentum always conserve if there's no net external force, but then the energy could have different cases. So if the KE conserve, okay, when there's a collision we call it elastic collision. When there's KE loss, we call them inelastic collision. For example, maybe when they collide there's a sound, okay, so that's the sound energy, so took away part of the KE from the system. And the other situation that you may have is called explosion. So explosion is a bit different. Think about things that is being stationary and suddenly it explode. So you can see that it somewhat gain KE. Momentum still conserve, okay, so then before that the momentum is zero. After that is split, okay, it will still have zero momentum in total. It's just that one is positive, one is negative. Remember, momentum is a factor. So how come they can have the KE introduced to the system? It was because there is chemical energy, okay, I mean it's an explosion. Now going back a little bit, we also would have a few keywords called impulse, which is a change in momentum, which if you are given a graph for force against time, then the curve, okay, the area under the curve will be the change in momentum, which is called the impulse as well. So you may use this relationship. You have this equation in a data booklet. Just pay attention that J is referring to impulse or change in momentum, okay, not something else. I try to look up why we use a simple J, but I cannot find why, okay. It just said that it's just to avoid confusion, okay, but I don't know why we just put delta P. Anyway, if you're HL student, I have a reminder for you here, okay, that you might be dealing with 2D problem in momentum, okay, so you need to resolve the velocity into vertical, horizontal, or the way that you like, and so to account for the total momentum in that axis. Okay, so this is something quite hidden in the syllabus that if you go back to check the subject guide, you'll find it out. Okay, it's written under guidance. So this is only applicable to HL. All right, I think we can finally go back to gravitational force. Okay, and so first of all, okay, some simplistic idea is if an object is close to planet surface, then we all know that the force, which is a weight, can be calculated by m times g. So that's everyone knowledge. So we also introduce a new idea in D1, that is Newton's law of gravitation, which is a more general equation that describes everything in gravitation. So there's an equation for that. This is the word definition. I'll recommend you to write it down and memorize it. I'm not going to read the words, okay, so you can refer to it by yourself. For the gravitational field, which will be considering the idea of per unit mass, and so again, this is a word definition. I recommend you to go for it, and then you have to recall them. So this is the idea of gravitational field, and so these two are definition, okay, and then if you try to put them together, you can derive this new equation, okay, but notice that this is the derived form. If you want to go back to take this general Newton's law of gravitation, you can always substitute the mass and the radius of the planet, and then you will find this reduced version. And I hope this makes sense, okay, that saying that this is a specific case while the Newton's law of gravitation is a more general case. We'll come back to this and talk about how this gravitational force will work with circular motion, okay, in orbital motion later on for 𝐿. And so now I think one thing we should look at is the gravitational field, okay. Here is a bit strange, okay, that the connection is a bit weird, okay. So for SL, you also need to know the field lines pattern, okay, including gravitational field, of course. Not in this video, but in a later video, we'll also talk about electric field and magnetic field as well. But generally, for the field lines, you need to know that the field line density represents the field strength, which is a magnitude. In terms of direction, each kind of field lines have their way, okay, of convention. So for gravitational, it's always towards the mass because it's attractive force always. For E field, we'll get to that again in the future, but if you want to know, it's positive, negative, while for magnetic field, it's north to south. Something for you to pay attention is how the scale will affect the shape. So the reason why on Earth surface we experience more or less a constant of acceleration is because the field are constant because of the scale. So as you can see, these are parallel line, so the density are pretty much constant. But if you put it in a more bigger scale, the Earth is more like a sphere, and therefore the field line will be radial, okay. So therefore there is a difference when you're going further and further away from the Earth. So you're expected to know how to draw them and tell the difference. And so that should be all for the SL student. Thank you. Now HL student, follow me with the next idea. So after we know about force and field, I think the most essential and tricky idea would be potential energy. And I although it's out of syllabus, as you can see here, I do recommend very much to everyone. If you haven't done the derivation, then you should do it. It's in the video, okay, so you can click this and then you can find the derivation if you're not sure how to do it. The main idea is you have to use the fundamental principle, the work done, okay, together with the gravitational force. The different thing in this GPE compared to the very early on one, okay, the MGH, that one, as I mentioned, is more general, okay, because the force is varying, and therefore we have to use calculus, we have to use integration to calculate it. It's not too difficult. If you study math, if you know calculus, then you probably can do it, okay. And so you substitute the force and you can then derive this equation with one requirement. You have to set the GPE at infinity as 0, okay, because you need to have a reference point. So with these two, then we can get to find the expression. Again, there's a word definition. I recommend you to go for it. And then conceptually, you need to be aware that it's a scalar, not a vector. Energy is a scalar. So the good thing is you don't have to care about the direction. So if you have more than one planet, let's say, with a small point mass, then you can just add them together, okay, for the energy. Same as potential, which we'll talk about now. So potential basically is take away the idea of mass, is per unit mass, as you can see in the word definition here, and therefore the equation is very similar but taking away one of the m. At the same time, the potential is really at the point. So if you want to calculate the work done, you have to find delta V, okay, and then of course multiply the m, so then the unit will become joule. So that's an equation that you have in the data booklet. And then moving onwards, we have something called the potential gradient, which might be quite challenging to some of you. So if you are not sure, you may want to again go back to look at the video. But essentially, as you can see from the equation, is to divide the distance. That's why it's called gradient, okay, because it's how fast the potential are changing. And the most important thing about them is it's very essential in a graph, that how a potential against distance, this graph, as I mentioned in the video, you can look at the slope of this curve, and then you can then basically take it as the acceleration, because as we can see here, G equals to this potential gradient. G is literally the gravitational field that we were talking about. So you can see everything are interconnected together. And so in this graph, then how steep, okay, the slope would means that the acceleration would be of a greater magnitude. So this is something that conceptually you need to know. Now going forward, we also have two more ideas. I would like to talk about escape velocity first. So escape velocity is quite straightforward. Okay, it's a ballistic motion. So a very simplified way, okay, different from rocket science. As you can tell, rocket has fuel, it will continue to propel. So the math and physics behind is more complicated, but here we're just talking about literally you project something, you flow something. It's like you throw a basketball. And the escape velocity word definition is like this. I make it quite extensive, although the math scheme usually do not require that much. I do believe, however, it's essential, okay, to have this long description. So basically it's talking about how much KE you need, okay, correspond to the speed, of course. So then you can reach to the infinity. So the KE can be sufficient enough, okay. And then if you try to go with this derivation, you will then get to the equation from the data booklet. Again, if you want to look at the derivation and know more, then there's a link, there's a video you can refer to. Now finally, we'll get to the orbital calculation. So again, it comes from the Newton's gravitational law and also the circular motion. Okay, as you can see, the orbital motion down here is actually circular motion. So we are then talking about very simplistic circular motion and orbital motion here, which is the gravitational force as the only source of the centripetal force. Okay, it's a perfect circle, and then the only force is the gravitational force. So putting the two equations together, okay, you can try as a practice. You can then derive the orbital speed, which is the one you have in the data booklet. The more challenging part will be something called the orbital energy equation, which is not in the data booklet. Okay, and then the equation look like this. The equation you have to talk about is potential energy, which essentially is the one that we have. But tricky thing is about the KE, which you can find from half mv squared, and then substitute the orbital speed into it. You can find the derivation if you are not sure in the video. Okay, and total energy is just a sum of the two. The interesting thing is they have a relationship. Okay, they look very similar, but they are off by a coefficient. Okay, which illustrated in this diagram here. They have a certain ratio basically. So using this idea, again, I'm not going into detail, but using this idea, then you can then deduce the effects. Okay, you can make prediction when during an orbital motion, of course. If an object is experiencing a viscous drag force, what would happen? This is something that students usually find counterintuitive. And so I will put down the general idea here is when you experience the drag force, it's definitely a work done, which taking energy away from the system. So the first thing that happens is the total energy will decrease, not KE. People always think that it's a KE get decreased because it's a drag, it's slow down. No. Okay, so the interesting thing is it's counterintuitive. So the total energy will decrease. And if you look at the equation, you'll find out the orbital radius decrease. Okay, and then because of keeping the radius decrease, KE will increase and then GPE will decrease. So basically it's sacrificing the GPE, and then the GPE part of it go for the work done against the frictional force, and the other part go to the KE. Okay, if it maintain as a orbital motion still. Oh, I'm sorry, I've totally forget I missed this. So from the gravitational potential, we learn how to do the calculation, and then for all the points which connect together with the same potential, we can have equal potential line or equal potential surfaces, depending on it's 1D or 2D, and therefore we can construct diagrams like this. One thing you should notice is the field line pattern and the equal potential surfaces or lines are perpendicular to each other. So again, you may have diagrams like this. This is for gravitation, but it's the same idea for electrical field. So we'll come back to this idea again in the next chapter. So here you have it. This is the summary for A1, A2, A3, and D1. So if you find anything you would like to suggest, I miss anything or I misinterpret anything, please let me know in the comment. If you find it useful, please also let me know, so then I can have the motivation to finish the rest of this series. Okay, I do enjoy making it, okay, but then it does really take quite a lot of time. So hopefully see you again next time. Bye.